Hello. We will see in this tutorial how to create a singular element, whose pressure drop coefficient varies according to certain variable parameters. We will take a valve as an example. The definition of the pressure drop coefficient of this valve is given according to the ratio H on D0, i.e. the opening height on D0, which is the diameter of the passage in the valve. The pressure drop coefficient is given on a graph here. Or on a data table. We are going to see how to create this new singular element with the singular element editor of the MechFlux Pro 3D software. The user will be able to modify the valve opening setting, and the pressure drop coefficient will be given according to this degree of openness. So it is a singular element with a variable pressure drop coefficient, depending on a variable parameter, here the degree of opening, accessible by the user. So we're going to use the singular element editor. Open the editor. We click on New Element, and here we select the option Adjustable according to variable parameters. When this option is selected, we activate the area for setting equations and variables. To define our pressure drop coefficient, we need two parameters, D0, which is the internal passage diameter of the valve, and H. By default, for a singular element, the software offers access to certain variables. dH the passage diameter, lambda, regular load loss coefficient linked to the length. The Reynolds number, and the roughness. These 5 variables are accessible, but not necessarily used. For our valve, we are missing a variable in this list. It is variable H. We are therefore going to create it. We are going to create the new variable, H, and we are going to give it its unit. We will get into the habit of giving the units of the variables, to be sure not to make mistakes when defining the parameters. In this example, we are creating a Loudlio valve with a passage diameter dH of 200 mm. We can vary this passage diameter, but by default, we give it a passage diameter of 200 mm. The maximum opening height will therefore be 200 mm, and when it is completely closed, it will be 0. The default value, let's say half open, 100 mm. Then we will set the user alerts. When the user goes out of the definition range of this parameter, there will be a software behavior that will be defined by what we are going to define here. If it tries to enter a value lower than the minimum value, we will force the value to the minimum. So if it tries to return to -200, 0 will be applied. And if it tries to exceed the maximum value, we will force the value to the maximum. So if we try to enter 500 mm, 200 mm will be applied. We have finished defining our variable H. We add to the list of a variable accessible in the expression. The head loss coefficient of this valve is given according to the combination of the variable H and D0. It is the ratio H divided by D0, which defines the head loss coefficient. So we are going to create a variable which will be the combination of variables made up of, we select H in the list of variables. This modifies this insert button. So here I select H. And I insert it in the description of the combination. There is a divisor ratio, it is H over BH. We select and insert the operator, and now insert DH. I have thus formulated the expression of the valid combined. I add it to the list of variables. After recording the minimum value, this combination, this ratio, has a maximum and a minimum which must be respected, otherwise there will be an alert. So what we are going to say is that the minimum value of the opening ratio is given here in our table, it is 0.25. And the maximum value is 1. Min, 0.25, max 1. We are going to determine what will happen in the event of a range exit. We are going to force the values. When we are going to be lower than 0.25, enforce the minimum value. When we are higher than 1, we will force the value to 1. And so we add this combined variable to the list of variables. And we created our combined variable, which will determine the pressure drop coefficient. We are now going to create the function of this pressure drop coefficient. We'll name it f. We'll assign a variable, which is h on dh. And we'll add this function in the list of functions. Now let's define the expression for this function. We see that the pressure drop coefficient is given on a curve. But we don't have an equation for this curve. So the element editor has a tool for defining expressions based on a curve. We will see how it works by clicking here to open the expression editor. And we are going to enter the values noted on the curve. Here, we have our data table. So the maximum and minimum values have been defined for this combined variable are found here 0, 25 and 1. Automatically, the software creates intermediate values. We will enter the corresponding values. For 0.25, we have 30. For 1, we have 0.15. For 0.40, we would have 12. So we don't necessarily have as many data insertion boxes as our table, but a polynomial will represent our curve. We are not obliged to enter all the values. For 0.55, we have 5.3. We can modify the proposed variable. For 0.5, we have 5.3. For 0.7, we have 1.5. We will start at 0.9. For 0.9, we have 0.3. We entered our data table, which defines the expression of our variable, defining the singular head loss coefficients. We now have the choice between various expressions, which stick more or less well with the data table. So to select the right expression, We will look at this small parameter, which is the maximum error observed, compared to the data entered. The fitted function is the exponential function that best represents our data table. We also have the graph on which we see the expression of the pressure drop coefficient. The adjusted function, which is here in purple, which goes from 30 to 0, with values below 0. It's not great here. We must not go below 0. What does the exponential function tell us? So the exponential function with square points is here. Never goes below 0. She is preferable. We will therefore select the exponential function. And so when you select the expression displayed at the top, which varies, and therefore shows the exponential function, validate and apply the expression displayed at the top. Here we have constructed the equation of the pressure drop coefficient of our valve. We could create several equations that add up, and in the final definition of the head loss coefficient. This tool can offer us multiple combinations to define a pressure drop coefficient. We are obliged to limit ourselves to a certain number of parameters. Which define a coefficient, but we can have multiple parameters. So here, we only have the parameter h on dh. Our function being determined, we are going to insert this function in the final definition of the pressure drop coefficient. So we select the function, and we insert the function. And we see that our pressure drop coefficient is defined. We apply, and we move on to setting the basic parameters. So we are going to set the diameter of our element, 200 millimeters. And we see that if one of these parameters is varied, the pressure drop coefficient will be varied. Here I will play on the h millimeter value. We said that the default value given for this element was 100 millimeters opening. I will go to 150 millimeters. The head loss coefficient is automatically adjusted according to its expression, which has been given here. It remains for us to name this new singular element Van Loudlio. We will select its image. Then we check that the image corresponds to the crossing of the fluid. Otherwise, one could flip or rotate the image. And if it's all good, we just have to save our valve. And here is our valve element saved in our library. So this definition of elements may seem a bit complex. But if you really want to have all the possibilities of creating pressure drop coefficients for multiple elements, this complexity is necessary. Otherwise, we are satisfied with fixed coefficients, which are more approximate. So we can close our element editor, and we'll see if it works. Here, for example, we said that we had made a valve for 200 mm. So we're going to create a small network. We're going to fit in a 200 mm pipe. That's it. And we insert our valve, so I select the conduit. In the singular elements of the library, I select the Loudlio valve that we created. I drag and drop onto the selected conduit. I find it here with the drawing that I applied. Now we are going to test this valve. We check the circulating fluid. Here, it's air. We're going to apply water. At a temperature of 10 degrees. Use this fluid. We do have water circulating in our network. And the outer fluid is air. We run a flow rate calculation at 200 cubic meters per hour to see the pressure drop generated in this system. Flux creates a theoretical generator, which generates enough pressure to balance the pressure drops in the elements at the desired flow rate, which is 200 cubic meters per hour. Then we see the pressure evolution scale. So here, the atmospheric pressure, we build pressure through the pressure generator, which could be a pump, a water column or whatever. We go through this pipe, so at this pressure, here, 80 millibars. And we see that our valve consumes and lowers the pressure, down to atmospheric pressure at the outlet. We can represent this with a piezometric graph, which gives more detailed information about the evolution of pressures. So we edit the piezometric graph. We display the pressure gains and losses. So we see the pressure gain, generated by our theoretical generator. We have very few pressure drops in the duct. We see that the delta is very small. And we have a strong head drop across the valve element. The table of data here below gives us the various parameters, losses of loads, and pressure inside the elements in entry and exit. Here we will see how to vary this famous variable parameter, which we gave for this valve element. To vary this parameter, we select the valve with the right button. Edit singular element. In the miscellaneous variable parameters, we modify this variable parameter. We will go here to a height of 50 mm, which corresponds to an aperture ratio of 0.24. So we saw that we set limits for the various parameters. The limit we set to the ratio H on DH was 0.25. So if I try to close my valve more, at 40 mm, we are reminded that the limit must be greater than 0.25. So we are forced to put a higher value, otherwise we are outside the scope of our element definition. So if you enter 50 mm, the pressure drop coefficient has been adjusted. It goes to 32. The adjustment is applied. the calculation is restarted. Before modifications, the pressure drop of the valve was less than 10,000 pascals. With an opening of 50 mm instead of 100 mm. We went to 50,832 pascals. We therefore have a pressure drop approximately 5 times greater. So that's it for this tutorial, at an advanced level, on the creation of singular elements with a variable coefficient, with the Mech Flux Pro 3D software.